Looking at the first question, it's pretty much very straightforward question. They would want you to find the Z and V value for a given substance at a given temperature and pressure. So in this question, they ask you to find Z and V for ethane at 57 degrees Celsius and 20 bar. What I will do is pretty much just list out every details that you have. For example, pretty much take out every value that is given so you wouldn't miss it. So I will just convert it to Kelvin first, and then P I could just put it to bar. I don't even have to convert it. So the first question, they want you to find the ideal gas equation. This is pretty much very straightforward. It's just PV equals to ZRT. But as we know, in ideal gas equation, we are ignoring the intermolecular forces. We don't take that forces into account, so we can just put Z equals to 1. The whole reason why we are finding this value of Z, if you notice, the whole reason why we are finding values of Z for each equation is because we are taking those intermolecular forces into account. For ideal gas equation, we are not really taking that into account, so we can just assume Z equals to 1. But for other equation as like virial equation or Rayleigh-Kwong equation, those equations take intermolecular forces into account, so we have to have like a different value of Z. So that's the whole reason why we are finding Z value and so on by iteration. Anyway, back to ideal gas equation. Pretty much just very straightforward. Just plugging in all these values are given into the PV equals to RT equation, and then by algebra, you just sub in those values and you will get this V equation. So Z equals to 1 and V equals to 1372.43. Next is the truncated virial equation. I believe this is the 3-parameter. Equation. I think so. This question is pretty easy because they already give you the equation, so you don't have to waste time by looking through the textbook for the equation, other than, of course, finding the values. So for truncated virial equation, you don't even have to go through the table, I think, since they already give value for B and C. It's just a matter of iteration. So again, we have this truncated virial equation. It's just a matter of plugging in this into this, and for the gas constant, you have to find a gas constant that is suitable with the equation. For, let's say, we have, what do we have here? V equals to cm cube mole -1, and P is in bar and T is in K. So for gas constant, you have to find values that correlate with the units used in this question. So I think that's the only important part for truncated virial equation that you have to pay attention to. So this is the value of R, value of gas constant that I chose, 83.14, since you can cancel out the values. And then just pretty much plugging in the values. But this is not your final answer, because you have to do iteration. I assume you guys have read my notes. You have to do iteration for every equation except the ideal gas equation. So as long as you see something like I plus 1, that means it's the first iteration. So you have to do iterations until you get a constant value. I'll try to plug in the video of the calculator pressing, so you'll get familiar with iterations. So it's just a matter of changing the values. So first value of V I get is 1230.29, and then I basically just plug in back into here the 1230.29 into this VI and this VI, and then I just keep pressing calculator until I get this constant value of 1212.55. And then once I get the value of V, the fixed volume, this is where iteration stops basically. Iteration stops here because the values are constant. and then since we already have value of v first, we know that they ask us to find z. So you have value of v, and then it's just matter of plugging it back into the PV equals to ZRT equation. Since you already have v, you already have p. R is you also have r. T you also have. So just matter of algebra and then rearranging equations to get z. I think this is the tricky part. I think this is the trickiest part that you guys are not familiar with, I think, which is the Redlich-Kwong equation, and then you have several other equations. But for this question, it is pretty much straightforward. I believe this whole question is very straightforward because you already give equations, so you don't have to bother wasting time by looking through the textbooks, except for finding value of alpha TR and the PC TC, and also value of sigma phi and all that. Let me just find it here. Actually, let me just go through my notes. Hold on. Yep, perfect. Okay, for Redlich-Kwong equation, you know that the full equation is z equals to 1 plus beta minus q beta times z minus beta over z plus blah blah blah. This is rearranging equation for z. For the main equation is actually p, but since they already rearranged it into z, you can just use this, honestly. So you just have to find the beta value and q value, which is given here, the table 3.1. So you guys just have to look at the Redlich-Kwong and see which value correlates. Yeah, for alpha TR, yeah, so look at the beta here. You need the value of this omega is 0.08664, and then just plug in here. Also for TR and PR, you just have to find the value of TC. Let me see. Yeah, you guys know the formula for TR, right? Just T over TC. PR is P over PC. So you just have to find the value of PC and TC from table. I can't remember which table. Yeah, you can just find yourself, honestly. So yeah, for beta, just find the TR, the reduced temperature, and the reduced pressure. Then you're just basically plugging in inside the beta equation. And also for Q, which is Redlich-Kwong. Redlich-Kwong is not really that complicated because it is also very straightforward. It's just TR power of -1/2, and then what else? The sigma, the epsilon, and the omega and phi is given here. So yeah, but also make sure that this is not your final answer, because you also have to do iteration for Redlich-Kwong equation, and Swarf, Redlich-Kwong, and Peng Robinson. So again, just I try to plug in the video of me pressing the calculator, so you guys are familiar with later during exam. Yeah, so basically just once you get this value for the first iteration, you get 0.8977, and then you just change it back to the value where the z stands at. So here first, I assume z equals to 1, and then 0.8977 here, and just change the value of 1 and 1 here, and then you get 0.8987, and then basically repeat the whole process until you get a constant value of z. The reason why I'm assuming z equals to 1 is because whenever we start with the equation like this, sometimes you don't know what value to assume first, right? So Yeah, for example here, we don't know what value to assume, but one easy way of like figuring this out, what value to assume, is we base our assumption, on ideal gases. So for ideal gas, we assume that Z equals to 1, right? Since we are ignoring intermolecular forces. But look, sometimes when the question does not give Z first, we need to find V first. So this is the equation for V. P equals to RT over V minus B minus A T over V plus epsilon B, V plus sigma B, whatever. So what value of V do we assume here? It's pretty tricky, but it's actually not that hard, since we're assuming our assumption on ideal gases. So we can just use PV equals ZRT. We know that P is given. We know that P is given, T is given, R is also given. Z equals to 1 for ideal gas. So just plug in the values to get V, and then just start our iteration with the value of V from ideal gas equation. So just substitute back the value of V ideal gas, which is VIG. Actually, this is actually VIG. For this V here, it's actually VIG. And then just pretty much just do iteration, honestly. So it's not really that hard. Basically from the calculation of Z earlier, from the first equation, from the third equation, I believe, from the Rayleigh's quantum, you just have to plug in the values again in your calculator. Since we're assuming Z equals to 1, this is the position of Z, Z1, Z2. So just press, and then this is your first iteration, right? So just plug in back into this, press answer, and then you get the second iteration, and then press equal again, just keep pressing until you get a constant value. So this is your constant value. So pretty much that's it. There's nothing really hard. For the second question, this is basically your heat of reaction. So let's just look at the equation that they gave. It's important to look through this question one by one, so that you guys don't miss out any details. So we know that the equation that they give, 4HCl plus O2 equals to 2H2O plus 2Cl2. And one important thing that we have to look at is 25% excess air, and the temperature of feed and temperature of outlet. And this one, you don't really have to look, except this adiabatically, and also no side reactions. So yeah. So for purpose of calculation, sketch the hypothetical process path and state assumptions. I believe I don't really have to go through hypothetical process path, because it's pretty much very simple. But I'll just go through very, very fast. Let's just see. So the first part is, we know that the substances enter at 338K, because 65 degrees Celsius, you change to Kelvin, you get 338K, and leaves at 650, 93K. But look, if you're going to use this table of C1 up to C4, you have to pay attention that the reference state for these tables is 298K. So you can't use this table unless your substance is at 298. So what you do is you have to bring in down 338 to 298K in order for you to use this table. And then the second path is basically the formation of products, which is H2O plus Cl2. Mind you, when they change formation, there is no increase in temperature. Only then, at the final path, you have to increase back to 923K. So in total, you have 3 paths. So yeah, just have to look, and just have to pay attention to that. Okay. So, and then for calculate the heat of reaction at 25 degrees Celsius, okay, this is pretty very simple, but heat of reaction, you have to know the difference between heat of reaction and CPDT is that for heat of reaction, heat of formation here, using heat of formation, the coefficient that is involved in heat of reaction is the stoichiometric coefficient. But for CPDT, the stoichiometric coefficient that is involved is the number of moles at feed or at output. So that's the difference. So for here, we know for HS, the value that they give here for heat of formation is that they are for stoichiometric coefficient of 1. So if they give 4 HCl, you basically have to times it by 4. And if they give 2 moles of H2O, you have to times it by 2. And you know that for heat of reaction, it's actually just heat of formation of product minus heat formation of reactant. Just find these values, plug in, times 4 or times 2, and then minus, you'll get this one. I believe those two questions are not really the hard part. It's just this part that's quite hard, I think. Yeah. So for C, determine the heat transfer associated with this overall process if 85% conversion can be achieved. So, yeah. What does conversion of 85% means? Is that when you carry out this reaction, if they say 100% conversion, that means 100% of reactants is fully converted to product. So there is no leftovers. But if 85% conversion, it means that only 85% of these reactants are converted into products. Alright, so it's not 100%. So there is excess. There is HCl at output. There is also O2 at output. So that is what is important. That's basically the definition of conversion. And one more thing is 25% excess air. We know that 25% excess, of course, if they say excess air, 25% only applies to O2. Okay, so what do I do when I see this question? Is basically first step is I draw a table and I list up all the substances involved in this reaction. We have HCl, we have O2, H2O, and Cl2. But one thing, one component that they don't obviously put out is the N2. But we know there is N2 because they said they use excess air. Unless they say 25% excess oxygen, then sure, there is no N2 here. But since they say it's air, so you have to take N2 into account. So first we have to figure out the basis. For this I use 4 moles of HCl for the sake of simplicity. Sure, you can use 1 mole, but it'll be confusing for you to do stoichiometric coefficient unless you're really smart at it. But if you want to play safe, just put 4 moles. Just use the stoichiometric coefficient that they give. Yeah. So for first is the end feed, the number of moles at the feed. So we know that it is 4 moles of HCl. There is no 1 mole of O2 because we know that there is 25% excess air. So sure, by mathematically calculating, sure, yes, it's actually just 1 mole. But since they said there is 25% excess air, which makes it 1.25 times 1. So we get 1.25 moles of oxygen. So that's actually 1.25 moles instead of only 1 moles of oxygen. Why I said 1 mole? Obviously, because by stoichiometric coefficient, we know that 4 moles of HCl reacts with 1 moles of O2. So by logic, there's only 1 mole. But since they said there is 25% excess air, you have to take that into account. So 1.25 times 1, you get 1.25 moles. For N2, why I times 79 over 21 is because of ratio for air, which is 21% O2 and 79% N2. So by ratio of 1.25 times 79 over 21, you'll get the N for N2. Yeah. Why I times 1.25 instead of 1 is because they said excess air. In air, we know that there's N2 and there's O2. So it's not only O2 that is in excess, N2 is also in excess. So I have to times 79/21 times 1.25 instead of only 1. So I get there is 44.7 moles of N2 at feed. Well, by logic, there is no H2O and Cl2 in feed. Also, yeah, okay. So now N reacted. So as I said earlier, N reacted has correlation with the fractional conversion, which means that there is 85% fractional conversion, which basically means 85% of reactants are converted into the product. So 0.85 times 4, you get 3.4. 3.4 moles are reacted. Yeah, 3.4 moles of reacted of 3.4 moles of HCl are reacted. And same thing here, 0.85 times 1, which is 0.85. The reason why I times 1 instead of 1.25 is because 1.25 is excess. So I times by 1. 1 is the moles of oxygen that is not in excess. So by stoichiometric coefficient, it's just 0.85 times 1 mole. So I get only 0.85 moles of oxygen that is reacted. And then for moles of output, this is just maths. N output is just N feed minus N reacted. You get excess of 0.6. Same for O2, which is 1.25 minus 0.85. I'll get 0.4. Since N2 is not involved in this reaction, so it's just 4.7 for in N output. And H2O, 1.7 is because, as we know, for stoichiometric coefficient, if they say that 4 moles of HCl produces 2 moles of H2O. So yeah. So by logic, if we don't take excess air into account, if we don't take the 85% conversion into account, it's actually just 2 moles of H2O that is formed, right? But since it is 85% conversion, which means that only 85% of HCl and O2 is converted into H2O and Cl2. So it's just 0.85 times 2, you get 1.7. So basically your table is complete. And then for CPDT, we know that what is the equation again? Yeah, we know that CPR is equals to A plus BT plus DT squared. So if you want to find CPDT for the whole process, you have to take summation of A, B, and D and see if it's given. Yeah. So we are only calculating for the first decrease in temperature, which is from 338K to 298K. So there is no reactant, there is no product involved. So the only substances that involve in the increase in temperature is just HCl, O2, and N2. So you just have to find the values of A, B, D for HCl, O2, and N2. And also you have to multiply the value of A, B, D by the number of moles. Yeah, that's what I explained earlier. The coefficient that is involved for CPDT is moles, and the coefficient that is involved in heat of reaction is the stoichiometric coefficient. And then yeah, just by finding the values, you get from 338 to 298K, you get this value of negative 11630.78. Also for heat of formation, yeah, and the next part is heat of formation at 298K. The reason why I times by 0.85 is because the heat of formation, basically what does heat of formation means that the heat liberated when you are forming these products from these reactants. So the reason why I don't times it by 0.85 here is because in A they don't say anything about only 85%. The assumption here is that 100% of reactant is converted into product. So I don't have to times it by 4. I don't have to times it by 0.85. But since in this question they said 85% conversion, so only 0.85 is only 85% of reactants are converted into products. So as I said earlier, the definition of heat of formation is basically the heat liberated when you are forming these products from these reactants, right? So if there's 85% conversion, which means that only 85% of heat liberated, which means that we're only finding 85% of heat liberated when you're forming these products. So again, fractional conversion plays an important role in finding heat of formation. So we know that the heat of formation here is negative 114,408 joules from earlier, so you just have to times it by 0.85 and you get these values. And then and then for the next part, actually I just have to put 3 here so it's easier to see. For the next part, we have to find the increase in temperature for the whole system from 298K to 923K. So for the whole system, we are involving products and reactants, right? So we have to find the ABD for products and reactants. So we are only looking at the output at the moles of we are looking at the moles only at the output. So so just 1.7 times A for H2O, blah blah, just do it, just common sense at this point, and then find the heat of reactant. And then also, since we know that it's adiabatic, so we can just safely assume as Ws equals to 0. This is just energy balance at this point, which is Q equals to Ws. This is open system, right? So you can just assume 0, and PE, there's no change in elevation, there's no change in velocity, so 0, 0, 0. So your final equation is Q equals to H, delta H. I don't have to times it by N here, is because we already times everything by the number of moles from 1 to 3. So I don't have to times it by moles again, since the value is already at joule. So delta H is basically just you plus everything. Actually, this is not HF, sorry, my bad. So H is just basically plus this one plus this one plus this one, and you get 77130.48 joules. Pretty much that's it, I guess.